Hi, welcome. This is lecture 8 of linear algebra. In this lecture, we're going to talk about the diagonalization of symmetric matrices and then the quadratic form, and at last, we shall go through the concept of the singular value decomposition, namely SVD. Okay, so recall that a matrix A is called symmetric if A transpose A transposes itself, coincides with itself, and such a matrix is necessarily to be a square matrix. And its main diagonal entries are arbitrary, but other than the main diagonal entries, the other entries occur in pair. Okay, so let us do an exercise. So if possible, we want to diagonalize the matrix given by A equals to 6 minus 2 minus 1 minus 2, 6 minus 1 minus 1 minus 1, 5. Okay, so our solution is that first we recall the characteristic equation of A. So we have 0 equals to A minus lambda I3 determinant. So that is just the determinant of 6 minus lambda minus 2 minus 1 minus 2, 6 minus lambda minus 1 minus 1 minus 1, 5 minus lambda. We shall now perform the calculation here. The result is lambda third minus lambda third plus 17 lambda second minus 19 lambda and plus 144. And this is just minus lambda minus 8 times lambda minus 6 and lambda minus 3. So we have three distinct eigenvalues. And for each eigenvalues, we can find an associated eigenspace. So we have V1 being minus 1, 1, 0, and lambda equals to 6. Our V2 is just minus 1, and 2. And when lambda is 3, we have our V3 being 1, 1, 1. Okay, and these three vectors form a basis for our 3, and in fact our V1, V2, and V3, and one can check they are mutually orthogonal. So this is an orthogonal side, and it is a basis for R3. So it is an orthogonal basis for our R3. Okay, and since in most applications the orthonormal bases are used for very useful for calculations, so we now normalize it to the form. So we normalize V1, V2, and V3 respectively, and we will guide. So the norm of V1 is obviously just square root of 2, so we have minus 1 over square root of 2 and 1 over square root of 2 and 0. And for U2, so that is U1, sorry. And U2 is, so we know the U2 has square root of 6, so it is minus 1 over square root of 6 and 2 over square root of 6. And similarly for our U3, it is just 1 over square root of 3, and this occur 3 times. Okay, and our diagonal, so our P, the invertible matrix could be just U1, U2, and U3, and our D is just with its main entry contains all the eigenvalues. So they are 8, 6, and 3, with all the other entries being zeros. And our A could be written as PDP inverse as usual, but this time P squared. And of course, we see that P has orthonormal columns, so P is an orthogonal matrix. So that is P inverse equals to PT, which is the definition of being an orthogonal matrix. So now we offer a theorem which explains why the eigenvectors are orthogonal, they correspond to, since they are corresponding to distinct eigenvalues, so this theorem is very useful. That is, if A is symmetric, then any two eigenvectors from different eigenspaces are orthogonal. We shall prove it. So if we write our V1 and V2, the eigenvectors correspond to distinct eigenvalues. So namely, we have correspond to lambda 1 and lambda 2 respectively, with our lambda 1 does not coincide with lambda 2. And we have that lambda V1 inner product, lambda 1 times the inner product of V1 and V2 equals to lambda 1 V1 transpose times just the normal multiplication, vector multiplication, since this is the definition of our inner product. And so this is by the definition of inner product. And since it is eigenvalue and eigenvector, the multiplication of these two, so it is just AV1 transpose times V2, since it is eigenvectors and their eigenvectors and eigenvalues. Okay, so this equals to our V1 transpose, A transpose. This is by the property of the operation transpose, V2, and it is just V1 transpose and A V2. So since our AT equals to A, it is symmetric. And also we have that still, since our V2 is an eigenvector, so that is just V1 transpose times inside lambda 2 V2. And that is lambda 2 V1 transpose V2, and that is lambda 2 times the inner product between V1 and V2. So it follows that on the left-hand side we have lambda 1 minus lambda 2 times V1 V2 is 0. So since our V1 and since our lambda 1 and lambda 2 are distinct, so it only means that our V1 and V2 has to be needs to have uh, 0 in the product. So the result follows from the linear independence. Actually, it follows from the fact that this guy does not vanish. Okay, and the special type of diagonalization in our first exercise is that it's very crucial for the theory of symmetric matrices. So this is the orthogonal diagonalizable. So we say that an n by n matrix A is orthogonally diagonalizable if there exists an P that is orthogonal matrix such that our P inverse equals to P transpose, and a diagonal matrix D such that our A equals to P D P inverse equals to P D P transpose. So yes, the only further restriction is to our P. That is, it is not only invertible but also orthogonal. So that means our P inverse equals to P transpose. And such a diagonalization requires unlinearly independent and orthonormal eigenvectors. The natural question is to ask when an matrix is orthogonally diagonalizable. So if A is orthogonally diagonalizable, so we have A transpose equals to PDP transpose, and that is P transpose transpose D transpose P transpose. And since our since transpose, then transpose is just itself, so we have P D, and D is diagonal, so we have PDP transpose, and it is just A, so we have it is symmetric. So now we will give a result, but now prove it that conversely, every symmetric matrices are also orthogonally diagonalizable. This is very useful. So that is an n by n matrix A is orthogonally diagonalizable if and only if A is symmetric, that is A transpose equals to A. And this theorem is rather amazing since the work in the previous lecture suggests that it is usually impossible to tell when a matrix is diagonalizable, but this is not the case for symmetric matrices. And now we shall show an example that treat a matrix whose eigenvalues which are different from our previous exercise that are distinct. This time they're not all distinct. So exercise 2. So we want to orthogonally diagonalize the matrix A given by 3, minus 2, 4, minus 2, 6, 2, 4, 2, 3. And we are given the characteristic equation being 0 equals to minus lambda minus 7 to the second and times lambda plus 2. So surely we have that the eigenvalues are 7 with multiplicity 2 and minus 2 with multiplicity 1. So for lambda equals to 7, we have two eigenvectors which are 1, 0, and 1, and V2 is minus 1 over 2, 1, and 0. And for lambda equals to minus 2, we have our V3 being minus 1 over 2, and 1. The calculations are not performed here. One can do it by themselves. It's very elementary. So we see that V1 and V2 are linearly independent, but they are not orthogonal. So how do we deal with this situation? Recall that the projection of V2 onto V1 is V2, V1, 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 V1. And the component of V2 orthogonal to V1 is given by, so namely Z2, which is Z2 minus V2, V1, 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 V1. So that is just, oh sorry, this is V2. So it is just minus 1 over 2 and 1, 0, minus minus 1 over 2 over 2, 1, 0, 1, and it gives us minus 1 over 4, 1, and 1 over 4. So our V1 and V2 is an orthogonal site in the eigenspace for lambda equals to 7. And since the eigenspace is two-dimensional with basis v1 and v2, so this is actually an orthogonal basis for the eigenspace by the basis theorem. For the eigenspace when lambda is 7. And if we normalize v1 and v2, we can have the orthonormal basis for the eigenspace when lambda is 7. So that is if we normalize it, so we have v1 being 1, 0, 1, so that is just 1 over square root of 2, 0, 1 over square root of 2. For our u2, it is just minus 1. It's minus 1 over, if we rescale it, it is minus 1, 4, and 1. So we have minus 1 over square root of 18, and 4 over square root of 18, and 1 over square root of 18. Orthonormal basis for the eigenspace when lambda is minus 2 is just u3 equals to 1 over 2v3 norm times 2v3. So that is 1/3 minus 2 minus 1, 2, and gives us minus 2/3 minus 1/3 and 2/3. Okay, so according to the previous theorem that if it is symmetric, then any eigenvectors form different eigenspaces are orthogonal. So we have that u3 is orthogonal to u2 and u1 respectively. So our u1, u2, 3 is an orthonormal side. So we can let our P be u1, u2, u3, and our D equals to 700,070,00 minus 2, and this is because the eigenvalue 7 has multiplicity of 2. So P is then we have that P orthogonally diagonalizes A with our A equals to P D P inverse. And the set of eigenvalues of a matrix A is sometimes called the spectrum of A. In fact, David Hilbert was the first to use the term spectrum to describe the set of eigenvalues of a linear operator in a series of papers starting in 1904. And he was apparently motivated by a loose analogy between the discrete sides of eigenvalues of certain, namely the integral operators and the atomic spectral lines discovered by physicists and in the 19th century. And so the spectrum is actually the set of eigenvalues, or it is sometimes called the point spectrum. And each eigenvalues need to carry the multiplicity. So so for a linear operator, namely T, the spectrum of T is denoted by sigma of T is the set of eigenvalues, namely lambda in C, such that T minus lambda fails to have a bounded inverse. So trivially, the complement of the spectrum is the solution, the resolution. Yeah, I think it's called the resolution site. Okay, so let us talk about the properties of the spectrum So this is actually called the spectral theorem for symmetric matrices. So an n by n symmetric matrix A has the following properties. The first is that A has n real eigenvalues. Of course, we need to count counting multiplicity. And the second is that the dimension of the eigenspace for each eigenvalue, namely lambda, requires the multiplicity of lambda as a root of the characteristic function equation. Moreover, the eigenspaces are mutually orthogonal. So in the sense that eigenvectors corresponding, to different eigenvalues are orthogonal. Furthermore, A is orthogonally diagonalizable, as we have seen in theorem 2. Okay, so suppose that A is orthogonally diagonalizable, and the columns of P are orthonormal eigenvectors. U1 up to UN are the orthonormal eigenvectors of the columns of P. The columns of P are orthonormal eigenvectors. Orthonormal eigenvectors of A, and the corresponding lambda 1 up to lambda n being the eigenvalues, and they are in the diagonal matrix D. So since our P inverse equals to P transpose, so that is orthogonally, it is an orthogonal matrix. So we have that A equals to P D P transpose equals to U1 UN, and so D is just lambda 1 to lambda n with all the remaining being 0, and the last term is U1 up to UN. Okay, so of course we need also to transpose each element inside it. So that gives us the lambda 1 U1 up to lambda n UN, and multiply our U1 transpose up to UN transpose. And if you use the column row expansion of the product, use the representation of the form with our A being lambda 1 U1 U1 transpose plus all the way down to lambda n UN transpose. So this leads to the definition of the spectral decomposition. So for an n by n matrix A in this form, where the columns of P are orthonormal eigenvectors U1 up to UN of A, and the corresponding eigenvalues are in the diagonal matrix D. The spectral decomposition of A is of the form this guy, since it breaks up A into pieces determined by the spectrum or the eigenvalues of A. And note that each term in this equation is an n by n matrix of rank 1. So for example, every column of the lambda 1, U1, U1 transpose is a multiple of U1. Moreover, each matrix UJ transpose is a projection matrix in the sense that for each x inside our Rn, we have the vector UJ transpose, then x. It is the orthogonal projection of x onto the subspace spanned by our UJ, where J ranges from 1 to n. The quadratic forms are derived naturally. The quadratic forms are functions that assign real numbers to vectors in a vector space, and they're often defined using a symmetric matrix. So let us define it. So quadratic forms are actually functions. So a quadratic form is actually a function, namely q from Rn to R. And it is of the form q of x equals to x transpose ax, where x is a vector in Rn, and A is an n by n symmetric matrix. So under this context, we say A is the matrix of the quadratic form. So the simplest example for non-zero quadratic form is the q of x being x transpose I x. So that gives us just the norm of x squared. Okay, so let's see an exercise. So if our x is x1, x2, and we want to compute x transpose ax for our, the first is that A equals 4003, and the second is A equals 2, 3, minus 2, minus 2, and 7. Okay, so for the first, our x transpose ax is just x1, x2 times 4003 and x1, x2. So it is just x1, x2 times x1, x2 times 4x1 and 3x2. So that gives us a 3x1 squared plus 3x2 squared. So we have no cross terms, that is, all the x1 times x2 with any coefficients vanishes. So that means the coefficient, this is not the eigenvalue, the coefficient of the cross product term vanishes. But the same thing not happen for the second one. So it is just x1, x2, and multiplied by our 3 minus 2, minus 2, and 7, and then multiply by x1 and x2. So it is our x1, x2 multiplied by 3x1 minus 2x2 and minus 2x1 plus 7x2. So we see that we have x1 times 3x1 minus 2x2 plus x2 times minus 2x1 plus 7x2. And this gives us 3x1 squared minus 2x1 x2 plus 2x2 x1 and then plus 7x2 squared. And since they are symmetric, so we have x1 squared minus sorry, this is a minus, not a plus. So minus 4x1 x2 and plus 7x2 squared. So we have the cross terms not being vanished. And this is bothering since our minus x1, x2 in our quadratic form it's not vanishing, right? So Let us consider another example. For our x lives in R3 and our quadratic form being 5x1 squared plus 3x2 squared plus 2x3 squared minus x1, x2, and then plus 8x2, x3. So this time we're still having the non-vanishing cross product terms, and we want to write the quadratic form as x transpose ax. So our solution is that since we want the coefficients of x1 squared, x2 squared, and x3 squared go on the main diagonal of A, so in order to make our asymmetric, the coefficients of xi, xj for our I not equal to j, of course 1 smaller equals to 1, j, okay. And this must be split evenly between both the ijth entry and the gi entry for our A. Since we have the coefficients of x1, x3 being 0, so we can check, we just offer the representation. So it is x1, x2, x3. The only matter is A. So we want our the coefficients of these guys go on the main diagonal. So we have 5, 3, and 2. And we want our since it has to be symmetric, right? So we want our ijth entry be split evenly. And since we have x1, x3 has term 0, so this one is 0. And for our minus x1, x2, we have a minus 1, and we need to split it into minus 1/2 and minus 1/2, so their sum is minus 1. And for x2, x3, we only need them to have the sum being 8. And these are 0 since the coefficients of x1, x3 is 0. So this is the desired quadratic form written in x transpose ax form. And in some cases, quadratic forms are easier to use when they have no cross product terms. So that's why I just said these guys are, they are very bothering. So when the matrix of the quadratic form is a diagonal matrix, this is what we are desiring. Unfortunately, the cross product term can be eliminated by making a suitable change of variable. So that is if our x represents a vector in Rn, and then change of variable is an equation of the form x equals to py, or y equals to p inverse x, where p is invertible and y is new variable in Rn, and here our y is just the coordinate vector of x relative to the basis of Rn determined by the columns of p. So if the change of variable is made in a quadratic form, namely x transpose ax, then we have x transpose ax equals to, since we are using the replacement, we have py transpose a and py, and this gives us y transpose p transpose a and py. So this equals to y transpose p transpose a, p, and then y. So the new matrix of the quadratic form is p transpose a, p, and since a is symmetric, and by our previous result that every if it is symmetric, then it is orthogonal diagonalizable. So there exists an orthogonal matrix P such that P transpose AP is a diagonal matrix, namely D. So if we denote PTAP as a D, so we have it is just YTDY. And this is the strategy for for us to eliminate the cross product terms. So let us do an exercise. Okay, so we want to make a change of variable that transforms the quadratic form for a equals to 3 minus 2 minus 2 and 7 into quadratic forms with no cross product terms. So the first step is to orthogonally diagonalize our A. So its eigenvalues turns out to be 3 and 7. So for lambda equals to 7, the associated eigenvector is 2 over square root 5 and minus 1 over square root 5. As you can see that we're already implying the unit eigenvectors, and the lambda equals to minus 7. The corresponding is 1 over square root 5 and 2 over square root 5. Okay, and these vectors are automatically orthogonal since they correspond to distinct eigenvalues, and it follows from our previous result. So they provide an orthonormal basis for R2. So that our P equals to 2 over square root of 5 minus 1 over square root of 5 and 1 over square root of 5, 2 over square root of 5, with our D being 3, 7 with zeros. Sorry, minus 7. This is our eigenvalues. Okay, so since our A equals to P D P inverse and our D equals to P inverse AP, which is P transpose AP, that is what we're desiring to find, and also since P is orthogonal. So now we apply the change of variable strategy. Change of variable. So a stable change for our variable is that x equals to py, where x equals to x1, x2, and our y is followed by y1 and y2. So we have that x1 squared minus 8x1, x2 minus 5x2 squared equals to x transpose ax equals to py transpose a py. And this is just y transpose p transpose a py equals to y transpose dy equals to 3y1 squared minus 7y2 squared. And we're done. Since we have now eliminated all the cross product terms. And to illustrate the meaning of the equality of the quadratic forms in the in this one, we can compute, for example, q of x for our x equals to minus 2 and 2. We're using the new quadratic form. So since our x equals to py, so y equals to p inverse x equals to p transpose x, so y equals to 2 over square root of 5, 1 over square root of 5, minus 1 over square root of 5, and 2 over square root of 5 times our x, that is minus 2 and 2. So this is 6 over square root of 5 and minus 2 over square root of 5. So therefore, by our new quadratic form, we have y1 squared minus 7y2 squared equals to 3 times y1, which is 6 square root of 5 squared minus 7 minus 2 square root of 5 squared, and this is 16. So yes, this exercise really illustrates the following theorem, which is called the principal axis theorem. So it states that this is called the principal axis theorem. So if A is an n by n symmetric matrix, then there is an orthogonal change of variable, namely x equals to py, that transforms our quadratic form namely x transpose A x into a quadratic form y transpose D y with no cross product terms. Yes, this theorem only states the existence, but the calculation is very a practical term. And the columns of P in this theorem are called the principal axis of the quadratic form x transpose Ax, and the vector y is just the coordinate vector of x related to the orthonormal basis of Rn given by these principal axes. And now we discuss the properties of the quadratic forms. So actually, if we let our A be an n by n symmetric matrix, then the quadratic form x transpose Ax is firstly, of course, the quadratic forms are dependent with the eigenvalue, so it is positive definite if and only if the eigenvalues of A are all positive. And similarly, it is negative definite if and only if the eigenvalues of A are all negative. And 3, it is indefinite if and only if it has both positive and negative eigenvalues. And the classification of a quadratic form is often carried to over to the matrix of the form. So a positive definite matrix A is a symmetric matrix for which its quadratic form x transpose Ax is positive definite, and same thing for negative definite and indefinite. So in some practical terms or in some like in statistics, we often say that given a positive semi-definite or positive definite matrix, it really means that the quadratic forms are having this property, or it has all the positive eigenvalues or non-negative eigenvalues. Okay, so now let's move to the singular value decomposition. Since the diagonalization theorem plays a part in many applications, but we do not know if all the matrices can be factored into the form A equals P inverse with D diagonal and the P invertible. A factorization of A equals to QD P inverse is possible for any n by n matrix. And a special factorization of this type is called the singular decomposition, which is very useful in application. So the singular value decomposition is based on the ordinary diagonalization that can so that is the absolute values of the eigenvalues of a matrix ensures the amount that a stretches or strings certain vectors. So that is if ax equals to lambda x and x has norm 1, then our ax norm equals to lambda x norm equals to lambda absolute value. So if lambda 1 is the largest eigenvalue, or it is the eigenvalue with the largest magnitude, then corresponding unit eigenvector v1, it identifies the direction in which the stretching effect of A is greatest. Of course, it may not be stretching, maybe shrinking. So that is the length of AX is maximized when X is just v1. And of course, if we have a minimalized, namely Vn, and lambda n and Vn, then the application of our A onto when X is just Vn, then the length is minimized. And this description of V1 and the absolute value of lambda 1 is an analog of the rectangular matrices, and it will lead to the so-called singular value decomposition. So we first define the singular values. So the singular values of A are the square roots of the eigenvalues of A transpose A, and denoted by namely sigma 1 up to sigma n, and they are arranged in a decreasing order. So that is our lambda I square root equals to sigma I for all our 1 smaller than equals to I and small equals to I. And the singular values of A are lengths of the vectors, namely AV1, AV2, AVN. So that is the how much it is shrinking or stretching, with our V1 up to our Vn is an orthonormal basis for our Rn consisting of eigenvectors of A transpose A, here our lambda 1 up to lambda n are the associated eigenvalues of A transpose A. Okay. And there is a theorem. So if we suppose that V1 up to Vn is an orthonormal basis of our Rn and consisting of eigenvectors of A transpose A, and is arranged in decreasing order. It is arranged so that the corresponding eigenvalues of our A transpose A satisfy lambda 1 greater equals all the way down lambda n. And suppose that R A has R non-zero singular values, then AV1 up to AVN is an orthogonal basis for the column space of A, and it has rank of A being R. So the composition of an n by n matrix involves an n by n diagonal matrix, namely a sigma of the form D 0, 0, 0, where D is R by R. Diagonal matrix for some R not exceeding the either the smaller m or the smaller of n, the mean of m or n. Okay, so now we arrive at the SVD, singular value decomposition. So A is n by n with its rank R. Then there exists an n by n matrix, namely sigma of the form sigma equals to D 0, 0, 0, for which the diagonal entries in D are the first are singular values of A. Okay. And with our sigma 1 greater than sigma 2, greater equals to all the way down to sigma R, which is positive. And there exists an m by m orthogonal matrix, namely U, and an n by n orthogonal matrix V, such that A equals to U sigma V transpose. Okay, so any factorization in this form with U and V orthogonal and sigma in this form, and positive entries in D is called a singular value decomposition of A. Note that we're assuming that it's a positive definite. So the matrices U and V are not uniquely determined by A, but the diagonal entries of sigma are necessarily the singular values of A. The columns of U in such a decomposition is called the left singular vectors of A, and similar V is the right singular vectors of A. So let us do an exercise to really find a singular value decomposition where our A is given by 1, minus 1, 2, minus 2 and 2, and 2 minus 2. So we want to find the singular value decomposition. So first, let us compute the A transpose A. So A transpose A equals to I will just ignore the calculation here. One can check by themselves. And this leads to the eigenvalues of A transpose A being either 18 or 0. So for lambda 1 equals to 18, we have the unit eigenvectors, v1 being 1 over square root of 2, that is we are normalizing it, and minus 1 over square root of 2. With our lambda 2 is 0, we have our v2 being 1 over square root of 2 and 1 over square root of 2. And these vectors form the columns of v, so our v is just v1, v2. And now we are done with v, and now we proceed to sigma. So that is, so first, our sigma 1, the singular value, is 3 square root 2, and our sigma 2 is 0. So since there is only one non-zero singular value, so the matrix D may be written as a single number. So that is, our sigma is just, our D diagonal is just 3 square root of 2. So the matrix, since the matrix sigma has to have the same size with A, so of course we need to have our D in its upper left corner, so it gives us the sigma is 3 square root of 2 with all the others being 0. Okay, so it left us to construct U. So if we are going to construct U, we first need to construct AV1 and AV2, as we seen in the definition and the theorem. So we have AV1 equals to 2 over square root of 2 minus 4 over square root of 2 and 4 over square root of 2. With our AV2 is just 0 entries. So one can verify that AV1, the norm of AV1 is indeed sigma 1, which is 3 times square root of 2. And AV2 is 0 since it has singular value 0. So the only column we found for U so far is U1 equals to 1 over sigma 1 AV1 equals to 1 over 3 square root of 2 AV1. And this gives us a 1 over 3 minus 2 over 3 and 2 over 3. And the other columns of U are found by extending the set U1 to an orthonormal basis for R3, since we need 3 of them. And in this case, we need two orthogonal unit vectors, namely U2 and U3, that are orthogonal to U1, and they are mutually orthogonal. And each vector must satisfy that U1 transpose X is 0, which is equivalent to our x1 minus 2x2 plus 2x3 is 0. So the basis for that solution is W1 being 2, 1, 0, and W2 being minus 2, 0, and 1. So now we can apply the Gram-Schmidt process to find, of course, with the normalization to W2 to find the orthogonal sides. So we have our U2 being 2 over square root of 5, 1 over square root of 5, and 0, with our U3 being minus 2 over square root of 45, 4 over square root of 45, and 5 over square root of 45. And so finally we set our U equals to U1, U2, and U3, and we have our A equals to U, sigma, and V transpose. And we just plug in our U, sigma, and V, and this is our singular value decomposition. And the four fundamental subspaces and the concept of singular values provide the final statement of the invertible matrix theorem. So A is an n by n matrix, and then the followings are equivalent. So the first is that A is invertible if and only if the column space of A is perp is 0. Of course, this happens if and only if the orthogonal complement of the of the null space is Rn itself, and for our row space is just Rn itself. And lastly, A has n non-zero singular values. Okay, so now we're done with all the basic concepts of linear algebra, and in the next lecture we shall briefly talk about the Jordan form, and then we will conclude all for our linear algebra lectures. Thank you for watching, and see you in the next lecture.